So welcome to second session of control systems, that is subject code 18EC 43. So in the previous class we have seen what do you mean by state, what do you mean by state vector and state equations and state variables and output equation. Okay, so after seeing the brief introduction about what is state variable and state vector, all those things, and also we have seen one of the one of the mechanical system how to represent in a state model. Okay, so after seeing all those things, so now in this session, so you'll see the state model for electrical systems. Okay, how to derive or how to generate the state model for the electrical systems. So let us take the problems examples one by one. So let us consider an example, the below the circuit what we are showing here. So this is the current source. There are three elements here: the current source, capacitor and inductor here, and this is resistor, the output resistor, and this is taken as current source will be taken as input source, and the Vout is a output source here. Okay, so if the circuit is like this, so then the first step is, there are the three steps what we are going to use in to derive the state model. The first step is, first we need to finalize how many state variables in the circuit. Okay, so we need to finalize the how many state variables. If you consider the above circuit, there are two state variables we will consider. So usually the state variables we will consider in terms of the storage elements. Okay, there are two storage elements here. So one is inductor, one more is the capacitor here, the current flowing through inductor and voltage across the capacitor. Okay, so the state variables for the above circuit we can give as x1 of t is equal to Vc, that is capacitor voltage, and x2 of t, the second variable, state variable, as inductive current. Okay, that is IL, current flowing through inductor. So now to generate the equations, to generate the state equations for means like x1t and x2 of t, so we need to apply the KCL. Okay, to get the equation for I of L. Okay, so now here the I of t is equal to, let the apply the KCL at node 1 at this point. If you apply the KCL, okay, I of t, whatever the current flowing through here, so I of t is equal to IC plus IL. So this is IL and this is IC. Okay, so IC plus IL. Okay, so now I of t is equal to IC plus IL. So IC can also be given in, that is C into dVc by dt. So derivative of the Vc, okay, with respect to dt is equal to whatever IC. So this IC is equal to I of t minus IL. Okay, so I of t we are represent, I of C we are representing in C into Vc of dt. So let us consider this as equation number 1. Okay, similarly apply the KVL. Okay, apply the KVL for the circuit. So L into DIL, okay, L into DIL by dt is equal to Vc minus V0. Okay, so add the inductor. So L into di by dt is equal to Vc minus V0. So we know that Vc minus V0 is nothing but VL into R. Okay, V0 is nothing but VL into R. Okay, so that is the load resistance. Okay, voltage across the resistor and the resistor value. This will be considered as equation number 2. The next, okay, step 1 is we need to find out state variables. The second one, we need to apply KCL and KVL. The third step, okay, third step here, whatever the equations we got above, okay, so we need to derive for x1 of t and x2 of t. Okay, so let us consider the first one. Okay, that is dVc by dt is equal to, so that is, so whatever we have considered here, so this, so this equation, so dVc by dVt is equal to 1 by C I of t minus 1 by C IL of t. Okay, the same equation we can give as, so dVc by dVt is equal to 1 minus 1 by IL of t plus 1 by c I of t. Okay, so whatever the derivative is there, okay, derivative with respect to capacitor voltage, so that we will, the first derivative we are considering as a x dot. So as we are saying in the previous session, so derivative we will consider as x dot. Okay, this will be x1 dot is equal to 1 by c x2, whatever IL we are considered as x2 of t, that is second state variable. Okay, and whatever I of t, it is nothing but input source. Okay, so both will be replaced with state variable and the input source. Similarly, dIL of dt is equal to 1 by L Vc minus 1 by IL into R. Okay, so the derivative of with respect to current, it will be considered as second state variable x2 dot is equal to 1 by x1. So Vc is nothing but the first variable, first state variable x1 of t minus R by L x2 of t. Okay, so now, and this is regarding the two state variables. But if you take the output equation, okay, so output equation, so V naught of t is equal to IL into R. Okay, so the V naught of t is equal to y of t, so y of t is equal to R will remain same, and IL is nothing but x2 of t, so that will be replaced with a state variable. So the finally we got equation 3, 4 and 5 here. Okay, so from these equations, okay, whatever we got the state equations, so from that we can write the state model. The state model is nothing but, so the x of t, okay, the state variable x of t is equal to, there are two state variables x1 dot and x2 dot. Okay, x1 dot and x2 dot is equal to, so this is nothing but the what we have seen the standard form, okay, for state equation, that is x dot of t is equal to a into x of t and b into u of t. Okay, so this is nothing but the coefficients, okay, coefficients with respect to the state variables, that is a. Okay, this we call as a vector, and this is x of t term, there are two state variables, and this is b output the coefficients, that is 1 by c and 0, and this is u of t. Okay, so this all is based on, so what we got in the previous equations, that is 1 by c, and here this is output coefficient, this is state coefficient. Okay, and this is similarly one more state coefficient, and this is also other the state coefficient. Okay, so this whatever state constants what we have seen. Okay, so that will represent in a standard form like ax of t plus b into u of t. Okay, the same thing we are just mentioning what is a vector and b vector. Okay, similarly like this, this is a state equation. Similarly the y of t, that is output equation, we can give as y of t is equal to 0 into r. Okay, 0 into r, that is nothing but c vector and two state variables, and there is no d term here. Okay, u of t equal to, that is d term coefficient is 0. Okay, so this is the state variable, sorry, state model for the whatever the circuit what we have considered. Okay, one is the state equation and one more is output equation in the form of the state model. Okay, so this is regarding the first circuit. So let us consider one more problem. This is for, we have the syllabus for this one, electrical, I mean we need to develop the state model for the electrical systems. Okay, the second circuits, so here we have considered the one resistor is there, inductor and one capacitor. Okay, so here in the earlier we have the two loops were there. Okay, here it is only the one loop. Okay, and here the state variables we are considered again as I of t, the current flowing through inductor, and x, that is x1 of t, and x2 of t as the voltage across the capacitor Vc. The same thing also we can give as V naught of t, as we can consider Vc as a V naught of t. Okay, so these two state variables, and then the step 2 we need to apply the KVL and KCL. Okay, so now we need to apply the KVL. So V of t is equal to, Vi of t is equal to I of t into R. Okay, and L into di by dt plus 1 by c integration of I of t dt, that is with respect to the capacitor. Okay, then whatever the since equation means, the third step what we need to do is we need to apply the, as it is only one loop, so KVL is sufficient, so we need to represent this equation into state variables. So di by dt is equal to, so whatever we got in the previous slide, okay, so this is di by dt. So di by dt, okay, if you take in the LHS side, so di by dt is equal to minus r by L into I of t, and 1 by L, whatever the integration term, that is 1 by C into integration of it dt, so that we can give as a v naught of t. So that will be replaced with v naught of t, and 1 by L v of t. Okay, the same thing what we can represent with state variables. So this will be derivative means x1 dot of t is equal to minus I minus r bar L x1 of t. So I of t is first variable, and v naught of t, that is nothing but vc of t is second variable, and vi of t is nothing but u of t. So this will be considered as the first state variable equation. Okay, so now as the vc is the second state variable, okay, we will consider v naught of t is equal to 1 by c integration of it into dt. So if you take a derivative of that, so derivative of v naught of t by dt is equal to 1 by c into I of t. Okay, so if you consider in the standard form, if you want to write x2 sorry, x2 of t is equal to 1 by c, okay, 1 by c x1 of t, that is I of t. So as there is only one state variable, no x2 term is there, so 0 into x2, and even u of t is not there, so 0 into u of t. So this will be considered as the second equation, because we need to find out basically in the step 3 the state variable equation. This is with respect to x1 of t, and this is with respect to x2 of t. Okay, two state variables. The next one, the same, once we got the state variable, we need to represent in the matrix form, that is what we know is x dot of t is equal to a into x of t plus b into u of t. Okay, so in that form, so this is x1 dot t and x2 dot of t, and this is a vector, and this is x of t, and this is b vector, and this is u of t. Okay, so the same thing we can give as the y naught of t. Okay, so this is the state variable, means state equation. Okay, if you take the output equation, so y of t is equal to v naught of t, that is nothing but 0 into x1 of t and 1 into, so v naught is nothing but second state variable, 0 into x of t and 1 into x2 of t and 0 u of t. Okay, so 0 and 1 coefficients for the c, and this is x of t, and d is 0, so that will be represented as ab vector like this, and c d vector is like this. Okay, so we have written the equation for the state model for the state equation 1, state equation, and the output equation. So both the coefficient matrix we can give as a, b, c, and d. Okay, so this will be representation of the state model for the second example. So let us move on to third example. So here we have again the two loops here, and first we need to consider how many state variables. So if you consider this particular circuit, there are two inductors are there and one capacitor. Okay, so there are three state variable will be there. So v of t is equal to u of t, x1 of t is equal to I1 of t, and x2 of t is equal to I2 of t, and x3 of t is equal to Vc, that is voltage across the capacitor. Okay, so as there are three storage elements, the three state variables will be there. Okay, so let us apply the KVL for this. Okay, so vi of t is equal to is the first loop. Okay, so vi of t is equal to L1 into di1 by dt into Vc of t. So that is L1 into di1 by dt and Vc of t. Okay, Same, if you take a derivative separately, so here dA I1 by dt is equal to minus 1 by L1 into Vc of t if you take this side, okay, plus 1 by L1 Vi of t. Okay, so here if you take, write the in coefficients, so x1 dot t is equal to derivative of di by dt, x1 dot of t is equal to 0. There is no what is that, there is no x1 term, okay, there is no x2 term, okay, only x3 term is there, 1 by minus L1 into x3 of t and 1 by L1 into u of t, because u of t is there and x3 term is there. Okay, so that is equation 1. And next one, let us consider the second loop, that is Vc of t is equal to L2 into di2 by dt into I2R. Okay, so the same di2 by dt is equal to, if you take with respect to dt separately as LHS, so R by L2 into I2, this term, plus 1 by L2 if you come this side, so 1 by L2 into Vc of t. Okay, again let us consider, write in a state equation form, so x2 of t is equal to x1 of t. Okay, x1 of t is not there, so x2 is there, I2 is nothing but x2 is there, and Vc is there, Vc is nothing but x3, and no u of t term is there. Okay, so the x2 of t is equal to, first variable is absent here, the second variable is there I2, and third variable Vc of t is there, and output input is not there, so that is 0 into u of t. So this will be considered as equation number 2. Okay, then again consider the last term. Okay, so Vc of t is equal to 1 by c, okay, 1 by c integration of I1 of t minus I2 of t. Okay, so this one we have considered with respect to second state variable, and this one is with respect to third state, that is Vc of t. Okay, so here if you take a derivative, so 1 by Ic into I1 of t minus I2 of t. Okay, so let us consider, write this term in a state equation format. So x3 dot of t is equal to 1 by c x1 of t, okay, that is I1 is there and I2 also is there, 1 by c x2 of t, and third term is 0 and input is not there. Okay, this will be considered as equation 3. Okay, and the last, so now we have considered 3 state variables x1, x2, x3. The remaining is the output equation y of t is equal to v naught of t into I of t into r. Okay, if you consider that format, x1 is 0, x2 is I of 2 of t and 0, and this is 0. Okay, so now here, so this will be output equation will be considered as equation 4. So all the things, whatever the 3 state variables and 1 output equation, all we are representing in the vector format as x dot of t is equal to a into x of t and b into u of t. This is a and this is b and this is u of t. Similarly, the output equation y of t 0, this is C matrix and there is no d term, this will be considered as 0. Okay, so this is a solution for the state model for the third diagram. Okay, and also there is one more possibility, that if we consider that is 2 output equation, like whatever the inductive term is there, so the second inductive term, that also you can, if you take that one as y1 of t and v naught if you take as y2 of t, then it will be considered as 2 output equations. In that case we can consider like this. Okay, otherwise, so we can consider only the one output, so which will be looking like this. So this state model. Okay, so like this we need to derive the state model for the electrical systems. Okay, there are 3 steps. So as we know, the first we need to derive, first we need to finalize how many state variables, then we need to decide whether is it KVL or KCL based on the circuit, whether we need to apply both KCL or KVL depending upon the circuit. After applying that, we need to get the state equations. So once we get the state equations, once we get the equations, then we need to convert into state equation. Then after the state equation, we need to represent in the vector format. Okay, so here we have considered the 3 examples. Okay,